Welcome back, dear students. So already we have covered the different theoretical aspects of characterization of biomass in the previous sessions. So let's do some problems based on this. Okay, this is our first problem. To determine the water equivalent of a bomb calorimeter, a 1.1651 gram of benzoic acid sample with a higher heating value of 6318 calorie per gram was used. The experiment produced a net corrected temperature rise of 3.077 degrees Celsius. The acid titration required 11.9 milliliter of standard alkali and 8 centimeter of PAR 45C10 nickel chromium fuse wire was consumed in the firing. Determine the water equivalent of bomb calorimeter. So this is our problem. So already we have studied the principle of bomb calorimeter and the equations for calculating the higher heating value. But this problem is not for calculating the higher heating value, but we are calibrating the bomb calorimeter for finding out the water equivalent, that is the heat capacity or water equivalent of calorimeter. For that we are using benzoic acid sample with a non-calorific value. Standardly we are using benzoic acid pellets with a calorific value of 6318 calorie per gram. So this is the problem. So first thing is you have to write down the given data. So here the calorific value or higher heating value, we are using capital H for that, is given 6318 calorie per gram. The mass of the sample is to be testing, that is the mass of benzoic acid is given capital M, that is 1.1651 gram. The temperature rise, so initial temperature and final temperature, that difference after conducting the test, delta T is given, that is 3.077 degrees Celsius. And other than this we have some error corrections. The first one is the acid formation. H2SO4 formation we are titrating with the standard alkali, and that quantity is 11.9 milliliter. So C1 will be equal to 11.9 milliliter. Now what is C2? C2 is another error correction which represents the sulfur content of the sample. So if the sulfur content is there more than 0.1%, we have to correct that also. But here there is no mentioning about the sulfur content, so we can take C2 equal to 0. Then another correction, that is C3 is a factor which corresponds to the length of burned fuse wire. So we are using fuse wire for ignition, so some part of it will be consumed, so we have to deduct that. So that is corresponding to C3, the length of fuse wire burned, that is given as 8 centimeter. So this is our problem. Now we have to use the equation. What is the equation? So before that, these will be the error correction factors. Capital E1 is C1 itself, C1 calorie, that means 11.9 calorie. And E2 we have the equation 13.7 into C2 into M, but C2 is 0 here, so E2 will be also 0. Then E3, according to the material, if we are using nickel chromium fuse wire, our equation will be E3 equal to 2.3 C3. So here 2.3 into 8 centimeter, so that will be 18.4 calories. So these are the error correction factors. Now this is our basic equation. Our calorific value is equal to W into delta T minus E1 minus E2 minus E3 divided by M. So calorific value, here we are using capital H for calorific value, and W is the heat capacity or water equivalent of calorific meter. Delta T is temperature rise, capital M is mass of the sample, and E1, E2, E3 are the error correction factors. Now in this we are to calculate capital W. So W, what will be W? W is calorific value into M plus E1 plus E2 plus E3 divided by delta T. So just substitute that. All are in calorie. No need to convert that into SI unit. We will get in calorie per degree Celsius per gram. So just substitute these values. All these values are known, and we will get this. So this is our answer. So the water equivalent of, or the heat capacity equivalent of this bomb calorimeter is 2402.1 calorie per degree Celsius. So with this is our final answer. Now we are moving to the second problem. Okay, this is our question. 1.5 gram of biomass sample is kept in a bomb of the calorimeter. The initial and final temperature of water in the bucket are 23 and 28 degrees Celsius respectively. The bucket wash is titrated against N/10 sodium carbonate and the titer value is 2.5 milliliter. The sulfur content in solid waste biomass is 2%. PAR 45C10 nickel chromium wire is used to ignite the biomass sample, and 4 cm of the wire is fused. The water equivalent of calorimeter is 2402 calorie per degree Celsius. Calculate the higher heating value of biomass. So this is a direct question. So this is similar to what we had to be done in the lab for determining the calorific value of a biomass sample. We have taken 1.5 gram of biomass. Test is conducted. Temperature rise is obtained. We know the water equivalent of calorimeter, and we know the factors for determining the error correction. So let's write the given data. So mass is given 1.5 gram. Then C1 corresponding to the factor for acid production, that is titrated by sodium carbonate here, and its value is 2.5 milliliter. So C1 is 2.5 milliliter. What is C2? C2 will be the sulfur content. So it's another error correction factor which represents the content of sulfur in the biomass. Here it is 2%. So that will be C2 will be 2. And C3 corresponding to the burning of fused wire. So here it is 4 centimeter. The length of burned fused wire is 4 centimeter. So C3 is 4 centimeter. And delta T is the temperature rise of calorimeter or water in the bucket, which is measured, and it will be 28 minus 23, 5 degrees. So 5 degree rise is obtained by conducting this test. So delta T is 5 degrees Celsius. And water equivalent of calorimeter is 2402 calorie per degree Celsius. So that is the constant which is obtained either from the supplier of calorimeter or is calibrated using some standard biomass like benzoic acid. So this is the given data. We have to just directly apply the equation. So before that, the error correction E1 E1 is directly equal to C1, so C1 is 2.5, that is converted into calories, so 2.5 calorie. E2 we have equation that is 13.7 into C2 into M, so therefore 13.7, C2 is 2% of sulfur in biomass, M is the mass of biomass, so 1.5, so that much calorie, that is 41.1 calorie. And E3, so we are using nickel chromium wire, it is 2.3 C3, so that depends on material of the wire. So if it is a platinum wire, this will be 0. So it is nickel chromium wire, we have this equation 2.3 C3, just multiply 2.3 with C3, that is the length of burned fused wire, 4 centimeter here, so that is equal to 9.2 calorie. Now directly we have this equation, that is calorific value is W, water equivalent or heat capacity of calorimeter, into delta T minus all the error correction calculated, minus E1 minus E2 minus E3 divided by M. Let's substitute here, so that will be 5 into temperature rise, 5 into 2402 water equivalent minus 2.5 minus 41.1 minus 9.2 divided by mass of the sample tested, that is 1.5. So just substitute here, there is no complexity. So we are getting calorific value as 7971 calorie per gram. So this is our answer. So in this we will be getting directly in calorie per gram. If you want to convert that into megajoule per kilogram or kilojoule per kilogram, we have to multiply with corresponding unit change factor. So this is the final answer. Now go for the third problem. A 2 gram of a dried agricultural waste is leached with benzene and ethanol mixture 2:1 volume at 60 degrees Celsius for 3 hours. After leaching, the residue is dried in a hot air oven 105 degrees Celsius to a constant weight of 1.8 gram. This dried material is put in a flask containing 150 milliliter of N/2 NaOH solution. The mixture is boiled for 3.5 hours with recycled distilled water. After this, the residue is washed with distilled water till all the sodium ions are removed and dried to a constant weight of 1.3 gram. Determine the extractives and hemicellulose content of this waste on dry basis. If moisture content of the waste is 15%, determine this value with respect to original sample. So this is what type of problem we have to calculate. This comes in the lignocellulosic composition of the biomass. So in lignocellulosic composition, we have determining extractives, percentage of extractives, hemicellulose, cellulose and lignin in a biomass. But in this question only we have to find out extractives and hemicellulose. The first two steps are only required. So this is not a complex problem, even though it's appeared to be a complex problem. It's a very easy problem. So there is only two procedures are there. First, we are determining the extractives by leaching it with benzene and ethanol mixture and then hot air oven drying. The mass is reduced. So we have, with the help of that two, initial mass and final mass, we can find out extractives. Then in the second step, the residue after the first step is going through certain process, that is with sodium hydroxide solution, and after distilling water and again removing sodium ions, etc. So again we are obtaining another mass. So we have 3 mass obtained, and from that we can very easily calculate the extractives and hemicellulose. So what are the given quantities initial weights, that is before the test, what is the mass? M0, we are denoting it as M0 before the test. The mass is 2 gram. Then the weight after extractive testing, that is the first process with ethanol and benzene mixing and drying in the hot air oven, what is the new weight? It is reduced to 1.8 grams. So M1 is 1.8 gram. Then after that, with sodium hydroxide solution, we have another mass, that is M3. The weight after hemicellulose separation, sorry, M2. So M2 is 1.3 grams. So these three masses are given. Initial mass M0, the extractive test, after the extractive test, the mass is reduced to 1.8 gram. Then again after hemicellulose separation, it is reduced to M2, that is 1.3 gram. The only thing is we have to just substitute the corresponding equation. So the extractive content will be W1 is equal to M0 minus M1, the difference in mass during the first test, divided by original mass M0 into 100. So that will be 2 minus 1.8 into 100 divided by 2. So 2 is M0, 1.8 is M1. So we are getting 10%. Now what is hemicellulose content? W2 hemicellulose content is M1 minus M2 divided by M0. Because in the hemicellulose test is carrying out after extractive test. So in this test, the initial mass is M1, final mass is M2. So M1 minus M2 divided by M0 into 100%. So substitute 1.8 minus 1.3 into 100 divided by M0, that is 2 again. So 25%. So this is the percentage of extractive and hemicellulose in this test. 10% and the 25%. And this question is having a second part, and suppose in this sample we have some moisture also. So if it is, we are having 25% moisture was there, what will be the value of extractive and hemicellulose? So if you are considering the moisture also, this is not the correct value because moisture also will be present. So what will be the new with respect to original material? This will be new extractive content, then will be. So we are obtaining 10%, but in that, sorry, not 25%, 15% is moisture. So in the question it is considered as 15% moisture. So what will be the actual extractive percentage? So it will be 10 into 85 divided by 100, because 15% we have moisture. So only in this 85% will be the remaining all factors. So we have to multiply this obtained value with the 85%, that is 85 by 100. So it will be 8.5 only. So if we see, we are considering moisture also, this value is reduced because moisture corresponding to 15%. So only we have the remaining 85%, we have extractive cellulose, hemicellulose and lignin. So we have to multiply the obtained value with the 85%, that is 85 divided by 100. Similarly, hemicellulose also, it is reduced to, we have obtained 25%, but if you are considering moisture, it will be 25 into 85 by 100, that is 21.25. So this is the second part answer. So first part, if you are, there is, we are considering as no moisture, but in the second part the moisture is given, that is 15%. So that will be reduced again. So this is the solution for this problem. Now moving on to another last problem. This is problem 4. So a biomass sample has following composition on mass basis: carbon 35.5%, hydrogen 4.8%, oxygen 25%, nitrogen 0.4, sulfur 15 percentage, so not 15, 0.15 percentage only, chlorine 0.55 percentage, moisture is 26 percentage, ash 7.6. Assume the average molecular weight of ash is 56. Determine the molecular formula and heating value on dry basis and as received basis of the biomass sample. Use the following equation for air heating value in megajoule per kilogram. We have an empirical equation 0.3516 into C plus 1.16225 into H minus 0.1109 into O plus 0.0628 into N plus 0.10465 into S. So this is the ultimate analysis result. So ultimate analysis, we are obtaining the percentage of carbon, nitrogen, oxygen, nitrogen, sulfur and chlorine and moisture and ash also. So if you add all this, we will get 100. So from this first thing, we have to calculate the molecular formula of biomass. Why this molecular formula is required? So every biomass or petrol or diesel and everything, we can write it as some Cx, Hy, Oz, etc. So if you obtain the molecular formula, we can calculate the stoichiometric air fuel ratio. That is very, very important. So we will study in later sessions. Stoichiometric ratio is very, very important because it determines what will be the airflow rate for gasification, what will be the airflow rate for pyrolysis, what will be the airflow rate for incineration. So all these are determined or based on the stoichiometric ratio of that biomass. So for obtaining the stoichiometric ratio, we must know the molecular formula of that biomass. So where that molecular formula can be obtained like this. So if the ultimate analysis and the moisture percentage and ash percentage is given, we can very easily calculate the molecular formula. So first write down the given composition, that is all the percentages given: carbon, oxygen, nitrogen, sulfur. So mainly carbon, hydrogen and oxygen are there. Nitrogen, sulfur, chlorine are very trace amount. Then moisture is given, ash is given. Another thing is we can write the molecular formula either as given or as measured like this, and also in the dry basis also. So in the dry basis means if we are continuously eating this biomass sample for a long period of time, moisture will be escaped or it will be removed. So in that we call it as a dry sample without any moisture. So then we have another equation, molecular formula is slightly changed. So we have to calculate both. So as received basis, that means moisture of 26 percentage, as well as dry basis. So dry basis means the moisture will not be there. Moisture will be 0 percentage, only these elements and ash will be present. So that two case will come in the practical example also. As received basis means there will be moisture. Dry basis means there will be 0 percentage moisture. So what is our next step? So already we are this percentage. Now consider 100 gram of biomass. 100 gram of biomass sample on received basis will have carbon 35.5 gram. That is correct. So carbon in 100 gram of biomass will be 35.5. Then what will be the moles? Mole of carbon we have to determine. Just divide this quantity by molecular weight. So molecular weight is 12. So 12 gram we have to divide. So carbon number of mole is 35 divided by 12, that is 2.958 moles. Similarly, all the elements we have to calculate the number of moles for writing out the molecular formula. Hydrogen 4.8 gram will be present in 100 gram, and its molecular weight is 1 gram. Hydrogen atom 1 gram, so 4.8 divided by 1, 4.8 moles. Oxygen is 25 gram, so 25 by 16. So remember one thing, we are not using oxygen molecule for this, oxygen atom only we have to consider. So the mass of oxygen atom is 16, mass of oxygen molecule is 32, but we have to consider O, that is oxygen atom. So 25 by 16, 1.5625 moles. Then nitrogen only 0.4 gram. So divide by that, 0.4 divided by 14, the mass of nitrogen atom, 0.0286 moles. Sulfur 0.15 gram, and its mass is 32, molecular weight. So 0.15 by 32, 0.00471 moles. Then chlorine is 0.55 gram, 0.55 divided by 35.5, 0.0155 moles. Then moisture is 26%, that means in 100 gram there will be 26 gram of moisture. Then what is the molecular mass of moisture? That is molecular mass of water, H2O. So hydrogen 1, so H2 means 2 plus oxygen 16, so 2 plus 16 we have 18, so 18 is the molecular mass of water. So 26 by 18, 1.444 moles. So all these are obtained by simply dividing the percentage given in the sample by its molecular weight. So we have to by heart some molecular weight of these basic components, oxygen, nitrogen, sulfur, etc. And finally ash. So ash molecular mass is given because ash is a combination of oxides, silicon dioxides, calcium oxide. So we don't know what is the mass of that. So mostly it will be given in the question. So the ash percentage molecular moles is 7.6 divided by 56, 0.1357 moles. So we have obtained all these in mole basis. We can now write the molecular formula of biomass. And if you want convert this H2O into again oxygen nitrogen, so H2O we have obtained is 1.444 moles. So in that oxygen will be 1.44 mole, hydrogen moles will be 2 into 1.44, that is 2.88 moles. So this is the mole number of moles of what H and O contributed from the moisture. So now we can write down the molecular formula. So we have two choice. So can we write like this: carbon C 2.958, hydrogen 4.8, oxygen 1.5625, nitrogen 0.0286, sulfur 0.0047, chlorine 0.01555, ash 0.1357, plus water, that is moisture 1.444. Or this is same as we can convert this moisture into hydrogen and oxygen and add this hydrogen and oxygen with the first two hydrogen and oxygen. We can write this way also. This is same as this also, carbon 2.958. Hydrogen is changed, hydrogen and oxygen we are adding in the second molecular formula. What we have done is we are adding hydrogen from the first, that is 4.8, plus hydrogen contributed by the water, moisture. So it is 2.888. So 4.8 plus 2.88 is 7.688. Similarly oxygen, first we have 1.5625 plus oxygen corresponding to water, that is 1.444. So now oxygen is 3.0065 and other things are same. So both are same. Either we can write it as first with water separately, or we can write in the second condition as also. So this equation is will be using in calculating the stoichiometric air fuel ratio this biomass, which is very, very useful. So now we have to find the air heating value based on the composition given. So for this, an empirical relation is given. So air heating value was on received basis, we can find out using this equation: 0.3516 into percentage of carbon plus 1.16225 into percentage of hydrogen minus 0.1109 into percentage of oxygen plus 0.0628 into percentage of nitrogen plus 0.10456 or 65 into percentage of sulfur. So this is the empirical relation given in the question. The only thing is we have to just substitute the percentage of carbon, hydrogen, oxygen, nitrogen and sulfur like this. So carbon is 35.5, hydrogen 4.8, oxygen is 25, nitrogen 0.4, sulfur is 0.15. So when substitute this, we will get the air heating value as 15.33 megajoule per kilogram. So in most of the journal etc., we can see they are finding the air heating value and lower heating value using empirical relations like this without conducting any experimental procedure. So this is the first part of the answer. Now we have to calculate all these on dry basis. So this was as received basis when the moisture is present, and on dry basis means we will remove completely the moisture. So what will be the composition on dry basis? It will not be the same. For example, if you take carbon on dry basis, it will be 35.5 into 100 divided by 100 minus 26, because the initial percentage of moisture is 26. So when we are removing the moisture, this will become 100 minus 26. So our new percentage of carbon will increase to 47.97 percentage. So that is very, very important. So on dry basis, all the composition of other carbon, hydrogen, oxygen, nitrogen, sulfur, ash etc. will increase. So carbon, the new percentage is 35.5 into 100 divided by 100 minus 26, because we are removing the all 26% of moisture on dry analysis. Similarly, hydrogen 4.8 into 100 divided by 100 minus 26, it is 6.49 percentage. Oxygen, it is 25 into 100 divided by 100 minus 26, 33.78. So oxygen is increased from 25 percentage to 33.78 percentage in dry basis. Nitrogen 0.4 into 100 divided by 100 minus 26, it is 0.54. Sulfur 0.15 into 100 divided by 100 minus 26 is equal to 0.203. Chlorine 0.55 into 100 divided by 100 minus 26, 0.74. And finally ash also increased. Ash initially 7.6 into 100 divided by 100 minus 26, it will be 10.27 percentage. So this is the new composition on dry basis. So we have to repeat the procedure. So the molecular formula will be changed. So again we have to repeat the same calculations based on this new percentage. So what will be the number of moles of carbon? So it will be this 47.97 divided by 12. Molecular weight of carbon 3.9775 moles. Hydrogen 6.49 divided by 1, 6.49. Oxygen 33.78 divided by 16, 2.11 mole. nitrogen is 0.54 divided by 14, 0.0386 mole. Sulfur 0.203 divided by 32, 0.00631 mole. Chlorine 0.74 divided by 35.5, 0.0208 moles. And finally ash 10.27 divided by 56, it is 0.1934 moles. So this is the new moles based on dry basis. So here there is no water because this is on dry basis, so no H2O will be there. So this will be our molecular formula: C 3.9975, H 6.49, O 2.111, N 0.0386, S 0.00631, chlorine 0.0208, ash 0.1834. So this is the molecular weight on dry basis. Now what will be the higher heating value? So higher heating value also we have to use the same equation, but we had composition is increased for carbon, nitrogen, oxygen, nitrogen, sulfur. We have to again substitute this new composition. So higher heating value, this is the equation given in the question. Let's substitute the new percentage of carbon, nitrogen, oxygen, nitrogen and sulfur. So this is the new percentage of carbon 47.97, hydrogen 6.49, oxygen 33.78, nitrogen 0.54, sulfur 0.203. So we will get 20.7 megajoule per kilogram. So that is a very important conclusion. You see that the heating value is increased. So on as received basis, the heating value was 15 point only megajoule per kilogram. Now you can see on dry basis, the same biomass, the heating value is increased to 20.71 megajoule per kilogram. So drying is an important pre-treatment in many biomass energy conversion process, especially like gasification, incineration, pyrolysis, etc. So if you have properly dried the biomass, the heating value will be increased. So that is a conclusion from this problem. So with this we are stopping these tutorials. You can practice the more similar problems from textbook and other material. Thank you.